This conference will now be recorded.
Good evening all. Today I am going to give a demo on DFT, which is designed for testability. So before we go into DFT, we will first understand what is VLSI. So VLSI stands for Very Large Scale Integration. Okay, VLSI stands for Very Large Scale Integration. So implementation of millions of switches in a small area. So millions of switches means millions of MOSFETs. So implementation of millions of MOSFETs in a small area is called as VLSI design. Okay. So motive of VLSI. So if suppose a particular company is designing a chip, okay, if suppose a particular company is designing a chip, so they will be having some primary conditions or primary targets that has to be met. Okay. So that is what is called as motive of VLSI. They will be having their own primary conditions and primary targets that has to be met. So if a particular company is designing their chip, that is what is called as motive of VLSI. So first thing is the high performance. Second thing is low power. So if we have low, we need to go for low power design in order to have longer battery life. Okay, so that is what is low power. So we need to go for low power design in order to achieve longer battery life. And then low area. So if the chip size is less, our product size will also be less. So that is why we will be going for low area. If our chip size is less, our product size will also be less. Okay. And this is how our chip will look like after manufacturing. So next we will discuss about the ASIC flow. So the full form of ASIC is Application Specific Integrated Circuit. So it is called as application specific integrated circuit because the IC, okay, the integrated circuit IC which we are designing, the chip which we are designing, it will be specific to a particular application. Okay, so the IC which we are designing, the chip which we are designing, it will be specific to a particular application. So that is why it is called as application specific integrated circuit. That is the full form of ASIC, application specific integrated circuit. The chip which we are designing, it will be specific to a particular application. So ASIC flow means it actually gives the steps which we need to follow for designing a chip. So whenever each company is designing their chip, so like each company, they will have to follow all these steps, the steps which is involved in the chip design while they are manufacturing a chip. Okay, so the steps, ASIC flow means it actually gives us the steps which we need to follow for designing a chip. Okay, it actually if a particular company is designing a chip, then they have to go through all these stages while they are designing the chip. So in the next slide, we will see about the various steps which is involved in the process of chip design. So that is nothing but the ASIC flow. The first is the design specification stage. So design specification stages, so like based on the application for which we are designing the chip. So they will be like architects, some experienced engineers called as architects, who will be deciding what has to be the speed, how many memory modules are required, how many processors are required, how many sensors are required, what has to be the power. So such kind of specifications will be decided by certain engineers called as architects. So that is what happens during the design specification stage. So after the design specification stage, we have the design code stage. So in the design code stage, the Verilog or VHDL code of the chip will be written. The functionality of the chip will be described in Verilog or VHDL form. So it will be in RTL form. So RTL means it will be in behavioral model and data flow level model. Behavioral model and data flow level model. That is what is the RTL form. Okay, behavioral and data flow level model. That is what is called as the RTL form. So during the design code stage, the functionality of the chip, it will be described in the RTL form. Okay, the functionality of the chip, it will be described in RTL form. The design code, okay, the functionality of the chip will be written. It will be done by a design team and it will be in RTL form. So it will be in like behavioral and data flow level model. So after the design team, we will be having the verification team. So verification team, they will be validating the functionality of the design to ensure that it meets the required specification and performs as intended. So that is what is the verification. So verification, they actually validate the design. Okay, they are actually used for, they will be validating the design. So they will be validating the functionality of the design to ensure that it meets the required specification and performs as intended. Okay, so that will be done by the verification team. So after the verification team, we have the synthesis. So synthesis team, they will be converting this behavioral and data flow level model code. This behavioral and data flow level model code, it will be converted into structural form. It will be converted into structural form, which is nothing but technology node specific gate level netlist. Technology node specific gate level netlist. Technology node specific gate level netlist. So technology node means it is like around like this one, 28 nanometer, 14 nanometer. That is what is called as a technology node. Okay. So the behavioral and data flow level form of code, what we are having, so that will be converted into the structural form. So it is nothing but technology node specific gate level netlist. That is what happens during synthesis. Okay. And after synthesis, we have the design for test team. So design for test team, DFT. We actually insert some test structures in the design during the pre-silicon stage, that is before manufacturing, to facilitate detection of manufacturing defects in the chip, to help in the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, we will be able to tell what manufacturing defect has actually caused the chip to fail. That is what is DFT. So DFT, it is to insert test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip, to help in the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, we will be able to tell what manufacturing chip has caused the chip, what manufacturing defect has caused the chip to fail. Okay. So that is what is DFT. We will discuss more about DFT in our later slides. And next is the PD, physical design. So physical design team, they convert the gate level netlist into layout form. Okay, physical design team, they convert gate level netlist into layout form. Okay. Next, it is the sign off. So next is the sign off. So during sign off, we will be doing like physical verification. We will be doing physical verification. Another one is STA and the third one is LEC, logical equivalence check. So physical verification, it is actually to verify the layout of the circuits. That is what is physical verification. So physical verification, it is to verify the layout of the circuits. STA is nothing but, as its name suggests, static timing analysis. So it is a method of validating the timing performance of a design by checking all possible paths for timing violations. So there will be various timing paths in our design. So all the timing paths will be like validated. So all the timing paths will be validated whether there are any timing violations or not. So that is what is the STA. So it is a method of validating the timing performance of a design by checking all possible paths for timing violations. And next is LEC. LEC is logical equivalence checks. Okay, LEC is logical equivalence check. So during logical equivalence check, we actually verify whether the final form of the design which we are having, whether it is equivalent to the original design or not. Okay, whether the final form of the design which we are having, whether it is equivalent to the original design or not. So why we need to do this LEC is, if you see in the process of chip design, our chip is undergoing a lot of changes in each and every stage. So in the beginning, we had first written the RTL code, that is in behavioral model or data flow level model code of the chip we have written. Okay, the RTL code of the chip has been written, RTL form. Okay, the design code of the chip has been written in RTL form. And then during synthesis, this behavioral and data flow level format code, it has been converted into structural form. So structural form means structural form or technology node specific gate level netlist. Okay, so the RTL code, the behavioral or data flow level model code, has been converted into structural form. So technology node specific gate level netlist. And also if you want to go for some low power design if you want to go, then we need to add some more structures like clock gating, retention registers, isolation cells. So such kind of some special cells have to be added. So those special cells will also be added at the time of synthesis. Okay. And DFT team, we will be adding our own structures like scan insertion, EDT insertion, BIST insertion. Like that, we will be adding our own structures into the design. And physical design, they will be converting the gate level netlist into layout form. Okay. So if you see, in all these stages, in each and every stage, design is undergoing a lot of changes. Okay. In each and every stage, our design is actually undergoing a lot of changes. So that is why we are checking whether the final form of the design, whether it is equivalent to the original design or not. So in order to check that, we will be going for LEC. Okay, logical equivalence check. So it is to check whether the final form of the design which we are having, whether it is equivalent to the original design or not, original form of the design or not. So why? Because in the process of chip design, our chip has undergone a lot of changes. Okay, during the process of chip design, our chip has undergone a lot of changes in each and every step. So that is why we are just checking whether the final form of the design which we are having, whether it is equivalent to the original design or not. So that is what will be done during LEC. And next is the tape out. So tape out means delivering the database to the manufacturing unit. Okay, delivering database to the manufacturing unit is nothing but tape out. And finally, we will be having the packaging and testing. So this packaging and testing, it will be happening after manufacturing. So packaging and testing is nothing but after manufacturing. So after manufacturing, this is how our chip will look like. This complete full circle is called as the wafer, and each small portion is called as a die. So packaging means covering this die with a protective layer. Okay, covering this die with a protective layer is called as packaging. And testing means it is to test whether our chip is good or not, whether our chip is having any manufacturing defects or not. That is what is called as testing. Okay, so covering this die, covering this small portion, covering this each and every small portion, this die with a protective layer is called as packaging. And testing means it is to test whether our chip is good or not, whether there are any manufacturing defects in our chip or not. That is what is testing. Okay. So in our later slides, we will discuss more about this design for test and then this testing in our later slides, much more in detail. Okay. So coming to the design for test. So as we have seen in the earlier slide, so DFT, it is to insert test structures in the design during the pre-silicon stage, that is before manufacturing, to facilitate, to help in the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so DFT, it is to insert test structures in the design during the pre-silicon stage, that is before manufacturing, to facilitate detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT team will be able to tell what manufacturing defect has caused the chip to fail. Okay. And next we will see the role of DFT engineer. So DFT engineers, we will be adding some designs into the IC to make sure that the testing is done properly, as we have seen in the earlier slide. And DFT engineers, they do not check the functionality of the chip. We rather check the quality of the chip. Okay, DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. So, for example, if you consider this circuit, this is a half adder circuit. So, functional verification engineer, they will check whether the half adder is functioning properly or not, whether this half adder is functioning as intended or not. Okay, just for an example, I have taken a small small circuit. So, functional verification engineer, they will check whether the half adder is functioning properly or not, whether the half adder is functioning as intended or not. That will be checked by the functional verification engineer. DFT engineers, we do not check the functionality. So what do? We check whether each and every net in the design, whether it is free of manufacturing defects or not. Okay, DFT engineers will check on each and every net of the design whether there are any manufacturing defects or not. That is what will be done by the DFT engineer. Okay, DFT engineer, they do not check the functionality of the chip. We rather check the quality of the chip. That is, say for example, in this case, we will be checking on each and every net whether there are any manufacturing defects or not. Okay, so that is what is the role of DFT engineers. And now we will see about this testing. So this testing, it is actually done after manufacturing. Okay, so in the ASIC flow we had seen, right, packaging and testing. So this is the testing which is done after manufacturing. After manufacturing. Okay, so testing is a process of determining whether a device is good or not. So device in our case, it is the chip. So it is to determine whether our chip is good or not, whether there are any manufacturing defects in our chip or not. That is what is testing. Okay. So testing includes test pattern generation, application and output evaluation. Okay. So this is what happens during testing. So this test pattern, it will be generated by the DFT engineer. So it will be generated before manufacturing itself. It will be generated before manufacturing itself during a process called as ATPG, automatic test pattern generation. Okay, so during the process of ATPG, the DFT engineers will be generating the patterns, automatic test pattern generation. It is a process. So during which the DFT engineers will be generating these test patterns. So these test patterns, it will be having input sequence and expected output. These test patterns will be having input sequence and expected output. Now here, this is the chip. So the input sequence, it will be applied onto our chip. Okay, the input sequence will be applied on our chip. And then the output of the chip output of the chip, it will be compared with the expected value. The output of the chip, it will be compared with the expected value. So we will be applying the input sequence to the chip, and then the output of the chip, it will be compared with the expected value. So if the chip output, if it is equal to the expected output, if it is equal to the expected output, then that means our chip is good. It doesn't have any manufacturing defect, because the output of the chip, it is same as that of the expected output, right? So it means that our chip is good, so it doesn't have any manufacturing defects. If the chip output, if it is not equal to the expected output, if the chip output, if it is different from the expected output, then it means that there is some manufacturing defects in the chip. Manufacturing defects are there. Our chip has failed. There are some manufacturing defects in the chip. Okay. So if a particular chip fails on the tester is nothing but the ATE. So after manufacturing, we will be testing our chips on the ATE, automatic test equipment. Okay. So that is what is the tester. So after manufacturing, we will be testing the chips on the ATE. Okay. So if a particular chip fails on the tester, the testing engineers, they cannot analyze it. Okay. So DFT engineers will analyze why the chip has failed using the inserted test structure. So DFT engineers will only be able to tell what manufacturing defect has caused the chip to fail. So if any chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so that is what happens at the time of testing. So during testing, the input sequence will be applied onto our chip, and then the output of the chip, it will be compared with the expected output. If both are same, if the output of the chip, if it is same as expected output, then that means our chip is good. It is not having any manufacturing defects. But if the output of the chip, if it is different from the expected output, if it is not equal to the expected output, then it means that our chip has failed and there are some manufacturing defects in the chip. Okay, and if suppose a particular chip fails, okay, after manufacturing at the time of testing, if suppose a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so this is what is testing. And these are the 4 possible outcomes of testing. So if a good IC, if it passes the test, it is called as true pass. Okay, good IC, if it passes the test. Okay, good IC, if it passes the test, it is called as true pass. A defective IC, if it fails the test, defective IC, if it fails the test, it is called as true reject. Now, if a defective IC, if it passes the test, if the defective IC passes the test, it is called as test escape. It is also called as under testing. Okay, defective IC, if it passes the test, it is called as test escape. It is also called as under testing. And if a good IC, if it fails the test, then it is called as yield loss. It is called as yield loss. It's also called as over testing. Okay, if a good IC, if it fails the test, it is called as yield loss. So it's called as over testing. Okay. So goal of good testing, it is actually to reduce the test escape and yield loss. Okay, goal of good testing, it is to reduce the test escape and yield loss. Okay, so yield means number of good chips divided by the total number of chips. Out of a total number of chips which has been manufactured, how many chips are good? That is what is yield. Okay, out of a total number of chips that has been manufactured, how many chips are good? That is what is called as yield. So yield means number of good chips divided by total number of chips. So out of a total number of chips which has been manufactured, how many chips are good? Okay, that is what is called as yield. Okay. And in the next slide, we will actually see what are manufacturing defects. So like we have seen like DFT engineers, so if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has actually caused the chip to fail, right? So that is what will be done by the DFT engineers. So like if a particular chip fails after manufacturing, what manufacturing defect has caused the chip to fail, that is what will be detected by the DFT team. Okay. So we will see what are these manufacturing defects. So manufacturing defects are nothing but the defects that are caused by process variations and random imperfections. Manufacturing defects are nothing but the defects that are caused by process variations and random imperfections. So process variations means like slight variation in the transistor channel length, metal interconnect width and thickness. So in that some slight variations. So if all those things happen, so those things it can actually impact the logical and timing performance. Okay, so slight variation in the transistor channel length, slight variation in the metal interconnect width and thickness. So all those things it will actually impact the logical and timing performance. So that is what is process variation. And random imperfections means unintended shorts, unintended opens. Those are called as random imperfections. Okay, it can result in opens and shorts. So unintentional shorts, unintentional opens. So that is what is called as random imperfections. Okay, so this is what is called as the manufacturing defects. So manufacturing defects are nothing but the defects that are caused by process variations and random imperfections. Okay. And next, let us try to understand the what is called as a defect, what is called as a fault, and what is called as an error. Because in our later sessions, like we will be using these terminologies like defect, fault, and error. These terminologies will be used. Okay, in our in our demo session also in the later slides we will be dealing with these terminologies, and also in our course also we will be dealing with these terminologies. So we will first try to understand what is a defect, what is the fault, and what is an error. So defect means unintended physical difference, between hardware implementation and its intended design. Okay, unintended physical difference between hardware implementation and its intended design. That is what is called as a defect. So say for example, according to the design intent, this is how it is there. So this is like one scan flop 1. So we'll discuss what is called as a scan flop. We will discuss later. So this is one scan flop 1. This is scan flop 2. So it is going as input to these AND gates. and output of this AND gate, it is again going to another scan point. So this is what is the design intent. This is what is our intended design. Okay, design intent or intended design. But during manufacturing, okay, during manufacturing, what has happened is unintentionally this B net got tied to ground. Unintentionally, this B net has got tied to ground. Okay, unintentionally, this B net has got tied to ground during manufacturing. Okay, so during manufacturing, this has happened unintentionally. This has happened unintentionally. Okay, so that is what is called as unintended physical difference between hardware implementation. So this is nothing but the hardware implementation. This is nothing but the hardware implementation. Okay, so unintended physical difference between hardware implementation and its intended design. That is what is called as defect. Okay, according to the design intent, this is what is my design intent. Okay, this is what is my intended design. But during manufacturing, we have seen, right, random imperfections we have seen in the previous slide, right? So during manufacturing, unintentionally, this B net of the AND gate has got tied to ground. So this has happened unintentionally. This is what is called as a defect. So unintended physical difference between hardware implementation and its intended design. Okay, so that is what is called as a defect. And next is nothing but faults. So logical representation of physical defects is called as fault. So the above physical defect, so the above physical or manufacturing defect, the above defect what we have seen, it is nothing but B net of AND gate, B net of AND gate is tied to ground, is tied to ground. This is the manufacturing defect. The above manufacturing defect what we have seen, it is nothing but B net of AND gate is tied to ground. That is what is the manufacturing defect. Now, this manufacturing defects logical representation. This manufacturing defects logical representation is called as a fault. Okay, this manufacturing defects logical representation is called as a fault. So if you want to represent this manufacturing defect logically, we can write it as B stuck at 0. B stuck at 0. Okay, so we can represent it logically like this. B stuck at 0. Okay, the above defect, the above what we have seen is the manufacturing defect. That is nothing but B net of AND gate is tied to ground. So if you want to logically represent this manufacturing defect, that is called as a fault. So the fault is nothing but B stuck at 0. So tied to ground is nothing but stuck at 0. It is always like stuck at 0. This is how you can represent it. Okay, B stuck at 0. Okay, so that is what is the logical representation of the fault. So logical representation of the defect. Logical representation of physical defects are called as faults. Okay, the above one is nothing but the physical defect. B net of AND gate is tied to ground. It is a physical defect. It's a manufacturing defect. So the logical representation of that manufacturing defect is called as fault. B stuck at 0. Okay, that is a fault. Okay, so we are just trying to understand the terminologies. So later when we use the terminologies, you should be like aware of what is a defect and what is a fault. You need to be aware of it. So in the later slides, we will be using these terminologies. Okay, so as of now, we are just trying to understand the terminology. In the later slides or in the later during the course, we will be using these terminologies. Okay. So defect is nothing but unintended physical difference between hardware implementation and its intended design. And logical representation of physical defect is called as faults. Okay. Error is nothing but wrong output signal value. Okay, wrong output signal value. Say for example, this is the intended design. This is actually the intended design. Intended design. So if you have 1 1, if you apply a 1 1 sequence here, so the output will be 1. But at the time of manufacturing, here what has happened? This has got tied to ground. This has got tied to ground. So Here you'll be, this is nothing but scan flop 1. This is nothing but scan flop 2. This is nothing but scan flop 3. This is scan flop 1. This is scan flop 2. This is scan flop 3. So you're applying a 1-1 pattern only in the scan flop 1 and scan flop 2. So the A net of this AND gate, this is nothing but A, B and Y. This is A, B and Y. A net will be getting a 1. B net it will be getting a 0. So here you are writing a 1 value only in the scan flop 2. But you will be getting a 0 because it has got unintentionally connected to ground. B net has got unintentionally connected to ground and output Y will be 0. So if you see, you are getting a wrong value at the output. You are getting a wrong value at the output. So the wrong value at the output because of the defect or fault is called as an error. Okay, the wrong value at the output is called as error. Okay. So yeah, this is what is called as error. So this is the expected output. The 1 is the expected output and the 0 which is coming here is nothing but the wrong value. The wrong value, the wrong output signal value, that is what is called as an error. Okay. And next we will try to understand the flow of DFT. So in flow of DFT, so first we will be having insertion. Insertion means adding of extra logic. So like scan insertion, EDT insertion, BIST insertion, boundary scan insertion, like that adding of extra logic. Okay, adding of extra logic is called as insertion. So you know, right? So DFT engineers, we will be inserting. So DFT engineers, we will be inserting some test structures into the design during the pre-silicon stage, that is before manufacturing, to help the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, we will be able to tell what manufacturing defect has actually caused the chip to fail. So insertion is nothing but the addition of that extra logic. Okay, addition of that extra logic is nothing but insertion. And next is generation. Generation is nothing but the generation of the pattern. So the pattern, it will be having input data as well as the expected output. That is what is a generation. And then validation. Validation is nothing but simulation. We'll be validating the patterns using simulation. So at the step, during the generation step, the tool will be generating the patterns. That is input data and expected output will be generated at the time of generation step. Validation is, it is to verify whether the patterns that is generated by the tool, whether it is correct or not. Okay, it is to, validation is nothing but to validate the patterns that is generated by the tool. Okay, it is to validate whether the patterns which are generated are correct or not, whether they are proper or not. Okay, it is to validate whether the patterns that are generated during this generation step, whether they are proper or not. That is what is the generation step, and that will be done with the help of a process called as simulations. Okay, so now you might get a doubt like the input sequence and expected output. This is what is the pattern, right? The pattern will be containing the input sequence and expected output. So this is actually generated by the tool, generated by the tool itself. So if it is generated by the tool, then why again we need to validate the patterns that are generated? Why do we have to check whether proper patterns are generated or not? Because if we write the input sequence and expected output, then like there can be some human error, so we need to validate it. But if the tool writes the pattern, if the patterns are generated by the tool, then why do we need to validate it? Why do we have to check if proper patterns are generated or not? If the patterns which is generated, whether they are proper or not, why do we have to validate it? So that is what is the need of simulation. We will discuss it in detail during our course. So when we are doing the simulation topic in our course, so we will discuss this need of simulations. Okay, why do we need to validate the patterns that are generated by the tool? Okay, so what is the need of simulations? So we will discuss that during our course in detail during the simulation topics. Okay. So insertion, it is to add the extra logic, additional logic into our design. Generation is nothing but to generate the patterns. That is, the pattern will be having the input sequence and then the expected output. And finally, we have the validation. So it is to validate the patterns that are generated by the tool. It is to check whether proper patterns have been generated or not. And that will be done with a process called as simulations. Okay. So this is our course outline. So first we will be covering scan insertion, then scan compression, which is nothing but EDT insertion, OCC on chip clock controller, ATPG, automatic test pattern generation, simulations, JTAG, joint test action group, BIST, memory built-in self-test, B-scan or boundary scan. So these are our course outline. Okay. So now I'll just give you a short overview of what each topic is. These are our course outline. IJTAG, IEEE 1687 standard, IJTAG is also covered. So in our main syllabus, I have not just kept it in the course outline because like in the demo, it is, you might not be able to understand about IJTAG because you need to have a clear understanding of JTAG to understand what is IJTAG. So that is why in the course outline, I have not kept it, but it will be covered in our regular DFT course, it will be covered. So these are the topics course outline which will be covered in our DFT syllabus. Okay, so now I will give you a short overview of what each stage is. Okay, each topic, what is it? We will just try to have a small overview of it. Okay. So first is the scan insertion. So scan insertion means it is a process where all the normal flops in the design, okay, it is a process where all the normal flops in the design are converted into scan flops, that is they are replaced with their scan equivalents, and a shift registered path is formed, a Q to SI path or a scan chain. Okay, so this is what is a scan chain. So these scan flops, they will be stitched into a scan chain. That is what is called as, that is what happens during scan insertion. All the normal flops in the design, they will be converted into scan flops, and these scan flops, they will be stitched into a scan chain. That is what is scan insertion. So the scan flop, if you see, it is nothing but a normal flop only, but at the input of a normal flop, you are having a mux. The select line of the mux is nothing but scan enable. Okay, the select line of this mux is scan enable. Okay. So now the scan enable only, it will be deciding whether functional input has to go into this flop or scan input has to be going into this flop. So we will discuss in detail what is the functional input, what is the scan input, what is scan enable signal. So like what is the what is the scan chain, how the scan chain operates. So all those things we will discuss in detail during our course. Okay, scan insertion means it is to convert all the normal flops into a design into scan flops, and it will be stitched into a scan chain. All these scan flops, it will be stitched into a scan chain. So it is actually done. So during our course, we will discuss in detail like what is a scan flop. Okay, what is a scan flop, and then what is a scan chain, how a scan flop operates, how a scan chain operates. All those things we will discuss in detail during our course. Okay, so scan flop is nothing but at the input of the normal flop, if you see there is one mux, so which is like selecting either functional input or scan input. So we will discuss what is a functional input, what is a scan input, all those things we will discuss in detail during our course. Okay. So now we will see what is the need of scan insertion. So why do we have to change all the normal flops into scan flops, and why do we have to stitch the scan flops into a scan chain? Why do we need to do the scan insertion? So scan insertion is actually done in order to gain controllability and observability of the design. That is nothing but in order to easily control and observe our design, we will be going for scan insertion. So scan insertion, the need of scan insertion is to gain controllability and observability of the design. In order to easily control and easily observe the design, we will be going for scan insertion. Okay. So we'll try to understand that point. What does it mean by easily controlling and easily observing a circuit? In order to easily control and observe a circuit, what does that mean? We will just try to understand with the help of an example. So consider that I'm having a design. So my design, so I'm having a 10-bit counter, and then I'm having a counter initialization circuit and then a counter observation circuit. Okay, in my design, I'm having a 10-bit counter. I'm having a counter initialization circuit and a counter observation circuit. Now we'll just assume that the counter is failing. Okay, we'll just assume that the counter is failing. That is after 999, instead of counting 1000, it is again counting 999. Okay, so we'll just assume that the counter is failing. That is, after counting 999, instead of counting 1000, it is again counting 999. So that is the reason why the counter is failing. So now we'll just try to see how many clock pulses are required by functional verification team and DFT team to find out that the counter is failing. Okay, how many clock pulses are required by functional verification team and DFT team to find out that the counter is failing. So if you see functional verification team, they require more than 1000 clock pulses to detect that the counter is failing. So why? As we already saw in the earlier slide, functional verification team, they check the functionality. Functional verification team check the functionality. So our counter, it is actually failing at the 1000th pulse. Okay, counter is failing at 1000th pulse. Because at the 1000th pulse only, the counter, instead of counting 1000, it is again counting 999. So the counter is failing at the 1000th pulse. Okay, the 1000th pulse only, instead of counting 1000, it is again counting 999. So counter is failing at the 1000th pulse. Okay, counter is failing at the 1000th pulse because at the 1000th pulse only, instead of counting 1000, it is again counting 999. Okay. So 1000 pulses are required. If it is failing at the 1000 pulse, 1000 pulses are required. Only when the counter goes till 1000 pulses, counts for 1000 pulses. At the 1000th pulse only it is failing, right? Instead of counting 1000, it is counting again 999. It is so counter is failing at the 1000th pulse, so the counter has to count for 1000 pulses. Okay, so at that point only functional verification team will be able to find out that the counter is failing because they are checking for the functionality. Okay, so counter is failing at the 1000th pulse. So 1000 pulses are required. And also some more pulses are required for counter initialization and counter observation. Some more clock pulses are required for counter initialization and counter observation. That is to bring the counter to the reset state. Okay, so in order to bring the counter to the initial state, that is what is called as counter initialization. Okay, in order to bring the counter to the initial state. And then counter observation is nothing but the output of the counter, it will be read. It has to be like the output of the counter, it has to be given to some register and the register has to be read. So that is what is called as counter observation. So some more clock pulses it will be required for counter initialization and counter observation. So altogether, functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Okay, so the counter is failing. Functional verification team, they check for the functionality. So counter is failing at the 1000th pulse. So at the 1000th pulse only, instead of counting 1000, it is again counting 999. So 1000 pulses are required for this itself. Okay, pulses are required for counter initialization and counter observation. That is in order to bring the counter to the initial state. That is what is called as counter initialization. Then the output of the counter, it has to be given to some register and the register has to be read. That is what is called as counter observation. So all about everything together. So functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Now DFT team, they will be approximately able to tell in the range of 100 clock pulses that the counter is failing. In the range of 100. So it can be somewhere around 80, 90, 100, 150. So in the range of 100 clock pulses itself, DFT team will be able to tell that the counter is failing. So functional verification team, they require more than 1000 pulses. DFT team, we approximately need in the range of 100 clock pulses. Okay, range of 100 clock pulses to tell that the counter is failing. Like 100, 150, 80, 90, like that is the range of 100 clock pulses. So here if you are able to see, functional verification team, they require more number of pulses. More pulses are required. More pulses. But DFT team, we require less pulses. Less clock pulses are required. So how DFT team is able to tell with this less number of clock pulses itself that the counter is failing? It is because we have gone for scan insertion. So that is what is called, that is what is the need of scan insertion. In order to easily control and observe our circuit, we will be going for scan insertion. And this one, how? So how DFT engineers are able to tell that the counter is failing in the range of 100 clock pulses itself? That will be discussed in the course. During the original course, it will be discussed. So in order to understand this, you first have to understand what is a scan cell, how a scan cell operates, what is a scan chain, how the scan chain operates. So if you understand these things, then you will be able to understand how we are able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So this is why we go for scan insertion, in order to easily control and observe our circuit. As we are able to easily control and observe our circuit only, we are able to tell that the counter is failing in this less number of clock cycles. And additionally, DFT team will also be able to tell what manufacturing defect has caused the counter to fail. Okay, what manufacturing defect has caused the counter to fail. So DFT engineers will be able to tell that additionally. Okay. So this is what is a scan insertion. And we will be discussing about scan DRCs in our original course. We will be discussing about the scan DRCs also. And then we will be discussing about edge mixing and domain mixing concept. And then an overview of scan chain reordering. Scan chain reordering will be performed by the physical design team, PD team. So we will just try to see an overview of scan chain reordering. Okay. So all these other topics will be covered during our syllabus in scan session. So next is scan compression. So scan compression means a single scan channel is internally divided into multiple scan chains. Okay, a single scan channel is internally divided into multiple scan chains. Or you can tell that this internal chains, they are compressed into channels. These internal chains are compressed into channels. Okay, you can tell that a single channel, it is internally divided into multiple chains. That is also fine. Okay, so this is what is a channel. This is a channel, and these are nothing but the chains. These are nothing but the internal chains. So you can tell that a single channel, it is internally divided into multiple scan chains. You can tell like that. Or you can also tell that the internal chains are compressed into channels. Okay, the internal chains, they are compressed into channels. That is what is called as scan compression. Okay, a scan channel, an external channel, you can tell that it is internally divided into multiple scan chains, or you can tell that the multiple scan chains, that is the internal chains, they are compressed into a channels. Okay, so both are correct. It is just like the way in which we are expressing it, but both the definitions are correct. Okay, so scan compression, why do we need to go for scan compression? Why do we need to compress this internal chains into external channels? Why do we have to do that? Okay, so it is actually to reduce the test time and to reduce the test data volume. Test data volume is nothing but the number of bits of patterns. Number of bits of patterns. So that is what is called as a test data volume. So in order to reduce the test time and in order to reduce the test data volume is nothing but the number of bits of patterns. That is why we go for scan compression. So scan compression means, a single channel, okay, an external channel, it is internally divided into multiple scan chains, or you can also tell like the internal chains are compressed into channels. Both the ways are correct. Okay. So why we need to go for scan compression? It is actually to reduce the test time and to reduce the test data volume. Test data volume is nothing but the number of bits of patterns. Okay. And how if we go for scan compression, we are able to reduce the test time and we are able to reduce the test data volume? We will discuss that in detail during our course. So we will give you logical explanation as well as with the help of formulas. We will try to see how if we go for scan compression, we are able to reduce the test time and also reduce the test data volume. That is nothing but the number of bits of patterns. Okay. So we will tell you logically, we will explain, and also with the help of formula, we will see the need of compression. And in order to achieve compression, okay, if you want to achieve compression, if we are using Descent tool, the mentor graphics tool, if you are using, we will be adding a logic called as EDT. The full form of EDT is embedded deterministic test. Okay, embedded deterministic test. Deterministic test. This is the full form of EDT. So in order to achieve scan compression, if we are using the Tessen tool, the mental graphics tool if we are using, we will be adding a logic called as EDT. Full form of EDT is embedded deterministic test. And these are the components of the EDT logic. So this is the decompressor logic. This is the compressor or compactor. Okay. And apart from this, bypass logic and controller logic will also be there, which is actually not depicted in this picture. Okay. So these are the components of the EDT logic, like the decompressor logic, the compressor logic, compressor, or it is also called as compactor, and then bypass logic and controller logic. So these are the four components of the EDT logic. Okay, everything is not depicted in this figure. So during our scan compression topic, we will be understanding like what is the role of decompressor, okay, what are the components inside decompressor and what role it plays in scan compression. Same way, what is the compactor or compressor, what is the internal logic of compactor or compressor, and what role it plays in the process of compression. Same way, controller, what are the components of controller, and then what role it plays in the process of compression, and same way the need of bypass logic. What is the bypass logic and what is the need of bypass logic? All those things we will try to understand during our scan compression topic. Okay, so in order to achieve scan compression, if you are using EDT, if you are using Tessen tool, mental graphics tool, we will be adding this logic EDT, embedded deterministic test. So that is what is called as EDT insertion. Okay. And next is ATPG. ATPG is automatic test pattern generation. ATPG is automatic test pattern generation. So as its name suggests, it is a process of generating test patterns for a given fault model. So fault model is nothing but stuck at TDF, transition delay fault model, PDF, that is path delay fault model, and IDDQ fault model. So automatic test pattern generation it is a process of generating test patterns for a given fault model. Okay, so as its name suggests. Okay, so during ATPG, what will happen? As its name suggests, test patterns will be generated. Okay, so during ATPG, the test patterns will be generated. So after manufacturing, if suppose there are any defects, okay, if suppose there are any manufacturing defects, these test patterns should have the capability to detect most of the manufacturing defects. Okay, so the test patterns it will be generated during ATPG, and here if you see after manufacturing, in order to test the chip, we are giving these test patterns, right, as we saw in the earlier slide. Okay, as we had seen in the earlier slide, here if you see during testing, this testing is done after manufacturing. So what is the test pattern we are applying to our chip? The test patterns which was generated at the time of ATPG. So those test pattern, that input sequence is only applied onto our chip. Okay. So during ATPG, as its name suggests, test patterns will be generated, and after manufacturing, if suppose there are any defects, these test patterns, whatever test patterns have been generated, right, that should have the capability to detect most of the manufacturing defects. Okay, if suppose there are any manufacturing defects, okay, in the chip, our test patterns, what is generated now, it should have the capability to detect most of those manufacturing defects. Okay, so at the time of ATPG, so how does our ATPG tool basically generate these test patterns? Okay, these test patterns, how does our ATPG tool generate? So how does it generate is, so our test patterns also, it should be having the capability to detect most of the defects, right? Most of the manufacturing defects, our test pattern should have the capability. Okay, so that is what we saw in the previous point, right? So after manufacturing, if suppose there are any defects, the test pattern what is generated now, it should have the capability to detect most of the manufacturing defects. So how is that ATPG tool able to generate those test patterns? So at the time of ATPG, tries to check if a particular defect occurs after manufacturing, will it get detected or not? Okay, so at the time of ATPG, our tool tries to check if a particular defect occurs after manufacturing, will it get detected or not? So now you all might have a question, like how does our tool know before manufacturing itself whether a particular manufacturing defect will get detected or not? So as of now, we have not manufactured our chip. So before manufacturing. So how does our tool know before manufacturing itself whether a particular manufacturing defect will get detected or not? So our tool know that. So our tool knows this because at the time of ATPG, it does a process called as fault simulation. It does the process called as fault simulation. So with the help of fault simulation only, our tool will be generating the test patterns. So that is why only the tool is able to make sure that these test patterns, whatever is generated, it is having the capability to detect most of the manufacturing defects. So if suppose there are any defects after manufacturing, our test pattern will have the capability to detect most of them. So how does our tool generate those kind of test patterns? That is because our tool performs a process called as fault simulation while it is generating the test pattern. So this is only the process of fault simulation. So we will learn it in detail during our syllabus. Okay, during our original course, we will learn it in detail, and also we will try to understand this with the help of some examples and illustrations. So as of now, you can just understand an overview of what is this fault simulation process. So at the time of ATPG, what we will be doing is we will be giving our design to the tool. Okay, we will be giving our design to the tool. So the ATPG tool, what will it do is it will keep this design. Okay, ATPG tool, it will keep the design, whatever design we are giving, right? It will keep this design. Okay, it will keep this design. And in its internal memory, everything will happen in its internal memory itself. And in its internal memory, it will create another copy of this design. In its internal memory, it will create another copy of this design. And in the created copy of the design, right, what it will do is, what are all the possible manufacturing defects that might occur in the design, everything the tool will induce it into that design. So that is what is called. So a logical representation of physical defect is what is called as fault, right? What is the fault? In the earlier slide we have seen, right? It is called as a fault list because logical representation of physical defect is called as fault. Okay. So what are all the possible manufacturing defects that might occur in a circuit, that might occur in a design? The tool will induce everything into that copy of the design. So it is called as fault because logical representation of physical defect is called as fault. And by doing this, what is the tool trying to do? The tool is actually trying to mimic all possible failure situations. It is trying to mimic all possible failure situations. By doing this, what is the tool trying to do? It is trying to mimic all possible failure situations that might occur after manufacturing. Okay. So what are all the possible manufacturing defects that might occur in a design? Everything the tool will induce it into the copy of the design which it has created. So by doing this, the tool is just trying to mimic all possible failure situations that might occur after manufacturing. And the design, what it has created, that is called as a faulty machine. This design, the copy of the design which the tool has created and in which it has induced all possible faults, that is called as a faulty machine. And the original design what we have given, it is called as good machine. It is called as good machine. Then what the tool does? The tool will apply patterns. The tool will apply input sequence for good machine. Okay, the tool will apply input sequence for good machine. And then the output of the good machine, it is called as the good value, or you can call it as the expected response. Okay, it is the good value. The tool will apply the patterns for the input sequence for the faulty machine. And then the output of the faulty machine, it is called as the faulty value. Then what does the tool do? the tool will compare the good value and then the faulty value. The tool will compare the good value and faulty value. So if good value and faulty value are different, mismatch means if both are different. If you see mismatch, good value and faulty value, it is comparing. Mismatch means if both are different. It will tell that those faults are detected faults. So we will try to understand this point. So say for example, for a particular pattern, for a particular fault, the good machine output, it is 1, and the faulty machine output, it is equal to 0. Just consider. So here what is happening? The good value, it is not equal to the faulty value. Both are different. Good value, it is not equal to the faulty value. Both are different. So what does this imply? What does this imply? It implies that if suppose this fault occurs after manufacturing, okay, the response of the chip along with the fault is 0, and expected value is 1. Okay, if good machine output is 1 and faulty machine output is 0, both are different. What does it imply? It implies that if suppose this fault occurs after manufacturing, the response of the chip along with this fault is 0 and the expected response is 1. So both are different. The response of the chip and then the expected value, both are different. So we are able to see that there is some problem in the chip. So we will be able to see that there is some problem in the chip. There is some problem in the chip, and hence those defects will get detected. If it occurs after manufacturing. So that is why only what the tool will do is, the tool will do the comparison between the good machine output and the faulty machine output. If both are different, it will place those faults into the detected class. So detected class of faults, what does it imply? It implies that if suppose any of the faults in this class occurs after manufacturing, it will get detected with the generated test pattern. Okay. And then good value and faulty value, the tool is comparing, and no mismatch. No mismatch means if both are same. So consider this case. So good value, it is equal to 1. Faulty value is also equal to 1. So which means both are same. Good value, it is same as faulty value. Then what does it imply? It implies that if suppose this fault occurs after manufacturing, okay, so what does this imply? It implies that if suppose this fault occurs after manufacturing, then the response of the chip along with the fault is 1, and the expected response is also 1. Expected output is also 1. Okay, what does it imply? If good value is equal to 1 and faulty machine value, if it is equal to 1, what does that imply? It implies that if suppose this fault occurs after manufacturing, the response of the chip along with the fault is 1, and the expected output is also equal to 1. Okay, the response of the chip along with this fault is also equal to 1. Expected response is also equal to 1. If the output of the chip along with the defect, if it is same as that of the expected response, then we are not able to see that there is some problem in the chip, right? We will not be able to see. Okay, the output of the chip along with the defect, if it is same as that of the expected value, then we will not be able to see that there is some problem in the chip. So those defects, it will not get detected. If suppose these defect occurs after manufacturing, it will not get detected. So the good value and faulty value, if both are same, It means that if the tool will place those faults into the undetected or not detected class. So not detected fault class means if suppose any of the faults in this class occurs after manufacturing, it will not get detected with the generated test pattern. So it means a good value and faulty value both are same. It means that the faults are not detected, will not get detected with the generated test pattern. Okay. So yeah, this is the procedure which the tool will be following for generating the test pattern. So for a particular fault, okay. So for a particular fault, if a particular pattern, if it gives good value, not equal to the faulty value, that is if it is different means, then what the tool will do, the tool will place that fault into the detected class and it will write out the pattern into the pattern list. Okay. So this is how the ATPG, this is the process which the ATPG tool will be using to generate the test patterns. Okay. And as the tool does this fault simulation only, the test pattern which is generated at the time of ATPG, it is having the capability to detect most of the defects. So after manufacturing, there are any defects. So our test pattern is having the capability to detect most of the defects. Okay. So at the time of ATPG, there are no actual failures. Okay, at the time of ATPG, there are no actual failures. The tool is just trying to mimic all possible failure situations that might occur after manufacturing. It is just trying to see the response of the chip. It is just doing this process in order to make sure that the test patterns which is generated will be having the capability to detect most of the manufacturing defects. So if suppose there are any defects after manufacturing, our test pattern should be having the capability to detect most of them. So fault simulation, so it is nothing but there are no actual failures. Okay, there are no actual failures. The tool is just trying to mimic all possible failure situations that might occur after manufacturing, and it's just trying to see the response of the chip. It is just trying to see whether the failure situations will get detected or not if suppose it occurs after manufacturing. Okay. So optimized set of test patterns are obtained during ATPG, which will be given to the tester for post-silicon validation. Okay. So how optimized set of patterns are generated, we will discuss it during our syllabus. Okay, during our course, we will see what is optimized set of patterns and how optimized set of patterns are generated during ATPG, we will see during our syllabus. So that is what will be given to the tester to test the chip after manufacturing. Okay. Next is simulation, as I told, to validate the patterns that was generated during ATPG to check whether, so simulations, it is actually to check whether proper patterns are generated or not. So simulation, it is actually to validate the patterns that were generated during ATPG. It is to check whether proper patterns are generated or not. And why we need to check that? Because the patterns are generated by the tool only. Then why do we need to check that? So we will understand that during our simulation topic. Okay, so it is actually to validate whether proper patterns are generated or not. It is used to validate the patterns that was generated during ATPG. Okay. And next is JTAG, Joint Test Action Group. Okay, JTAG. So JTAG is an IEEE standard, IEEE 1149.1 standard. And why DFT engineers we use JTAG is, one is to minimize the number of ports from the top level, and the other one is to achieve boundary scan. These are the two needs of JTAG. Okay, one need is to minimize the number of ports from the top level, and the other one is to achieve boundary scan. Okay, so I'll first understand how with the help of JTAG we are able to minimize the number of ports from the top level. So here if you see, I have kept a list of some important signals. Okay, these are some list of some important signals I have kept. So these are some list of important signals, just a list of important signals alone. Apart from this, there will be many more signals like this. Okay, apart from these signals, there will be many more signals. These are just some important signals. Apart from this, there will be many more signals like this. Now, if all these signals are to be controlled from the top level, to allocate a top level port, okay, if we have to allocate a top level port in order to control each of these signals, then what will happen? number of ports on top level will increase drastically. Number of top level ports will increase drastically. Number of top level ports will increase drastically. Okay. So, if these are some list of important signals, there will be many more signals like this. So, if all these signals are to be controlled from the top level, if we allocate a top level port in order to control each and every signal, then what will happen? The number of top level ports, it will increase drastically. So the number of ports which is allocated for DFT will be limited. Okay, the number of top level ports which is allocated for DFT will be limited. So what do? We actually make use of this JTAG. We actually make use of this JTAG in order to internally control these signals. Internally control static signals. In order to internally control static signals. Okay, static signals means they are the signals that retain the same value throughout the run. Okay, static signals means they are the signals that maintain the same value throughout the run. Okay, so with the help of JTAG, we will internally control the static signals. So as we are internally controlling these static signals with the help of JTAG, in order to control all these static signals, we require only 5 top level ports. The 5 ports which is required for JTAG. Okay, the 5 JTAG ports like TDI, TDO, TMS, TClock and one optional T reset. So these are the 5 signals of JTAG. So in order, these 5 signals only will be controlled from top level. So in order to, if you use JTAG to internally control these static signals, okay, if you use JTAG to internally control these static signals, then we just require only 5 top level ports. So 5 the ports which is required for JTAG. Okay, only 5 top level ports will be required in order to control all these signals. Okay, so that is how we are able to minimize the number of ports from level. Okay. So how with the help of JTAG we are able to internally control the static signals? We will discuss that later during our course. So for that we need to understand the structure of JTAG. Okay, so we will discuss that in detail in our course. Okay. And also to achieve boundary scan, one need of JTAG it is to minimize the number of top level ports. The other need of JTAG is to achieve boundary scan. Okay. So what is boundary scan? We will first understand. So in this case, there are 3 chips. So chip 1, chip 2, chip 3. So now these 3 chips, they have been manufactured. And after manufacturing, there will be one testing, right? As we discussed in the first few slides. In the first few slides, we had discussed about the testing, right? So what had happened? First, these chips, it will be tested on the tester or the ATE. Okay. So like this chip 1, chip 2, chip 3, all these chips have been tested on the ATE. So input will be applied to the chip and the output of the chip will be going back again to the ATE. Input will be applied to the chip, output of the chip will be again going to the ATE, like this. So the chips are first tested on the ATE. Now when these chips, this chip 1, chip 2, chip 3 in this example, when they are tested on the ATE, all these 3 chips have passed their test. All these 3 chips have passed their test. So it means that if the chips have passed their test, it means that chip 1, chip 2, chip 3 don't have any manufacturing defects. Don't have any manufacturing defects. They are good. Okay. So chip 1, chip 2, chip 3, they are first after manufacturing, they are first tested on the tester. And all these chips have passed. That means they are good. They don't have any manufacturing defects. Okay. After this, what is happening is these chips are placed on a board. Board is nothing but the PCB board. These chips are placed on the PCB board. Chip 1, chip 2, chip 3, they are placed on the PCB board. And then the interconnection between these chips and all are formed. Like this. Okay. Now next what is happening? Board is tested. Now when the board is tested, what is happening? It is failing. Board is failing. So that is what is said here. Chip 1, chip 2, chip 3 are properly passing the test of DFT, that is on the ATE. All these 3 chips have passed, which means they don't have any manufacturing defect. But still the board is failing. Okay. So after this testing, these chips will be placed on the board and then the interconnections would be formed. And now when the board is being tested, it is failing. So chip 1, chip 2, chip 3, they are not having any manufacturing defects because they have already passed their test.at. Then why is the board testing failing now? It is because there can be some manufacturing defects in the interconnections between the chips. So it can be due to manufacturing defects in the interconnection between two chips. Interconnection between two chips. Okay, the board is failing because there can be some manufacturing defects in the interconnection between two chips. So this is why we go for boundary scan. So boundary scan, it is to test the interconnection between two chips. It is to test the interconnections between the two chips. This is why we go for boundary scan. So how with the help of JTAG we are able to do the boundary scan? All those things we will discuss it during our course. So for that you need to understand what is a JTAG first. So just have just given you an overview of what is a boundary scan. So in order to test the interconnection between two chips, we will be going for boundary scan. Okay. So how with the help of JTAG we are able to do the boundary scan? So we will discuss it during our course. Okay. And next is MBIST, memory built-in self-test. So memories, they are actually a combination of analog and digital components. So we use separate MBIST technique to test the memories. Okay. So why we need separate MBIST technique? So flops and combo logics, they are tested using ATPG itself. They are tested during ATPG itself. But why for memories we need separate technique, MBIST technique? Why it is required? We will discuss it during the course. Okay. Why for memories we are having a separate MBIST technique? Okay. That we will discuss it during our course. So in order to test the memories only, we will be going for MBIST. Okay, so during our course, we will discuss what are all the memory fault models. Then we will discuss about what some basic algorithms we will discuss in order to detect the faults in the memory. And then we will understand about IJTAG. And then we will understand about Tessent MBIST. How is MBIST implemented in Tessent tool? We will understand that, okay, in the metagraphics tool. Okay, so all these things we will understand it during the MBIST topic. At that time itself, we will be able to understand why we are using separate MBIST technique in order to test the memory. Okay. And whatever we saw earlier was the theory, okay, theory overview. And for labs, we will see. So labs, we will be covering the IJTAG insertion, MBIST insertion, scan insertion. So basically, there are two approaches for scan insertion. One is the top down and the other one is the hierarchical scan. So both the approaches we will be covering. Next is EDT and OCC insertion, ATPG, automatic test pattern generation, ATPG and MBIST simulation. So all these topics will be covered in our labs. Okay. So simulations, we will actually be covering only no timing simulations. We will be covering only no timing simulations. Okay. So why? Because in order to do the timing simulations, one input file is required called as the SDF file, standard delay format. SDF file is required. So in our labs, we are not having the SDF file. So that is why we will not be covering the timing simulations. We will be covering the practicals of only no timing simulations. Okay. And this is how our labs are structured. Our labs are structured into 4 levels, level 1, level 2, level 3 and level 4. So level 1 projects, totally we are having 11 test cases. So these are like small designs. So around like maximum of 100 flops would be there. So small designs. Okay. So we will be performing scan insertion for these 11 test cases. And in level 2 projects, for the same 11 test cases, we will be performing the EDT insertion, which is nothing but scan compression, ATPG, so automatic test pattern generation and simulations. For all those 11 test cases, we will be performing it. So these are small test cases, maximum of around 100 flops will be there. Level 3 and level 4 projects are more complex designs. Okay, complexity is high. Okay, so level 3 projects, we will be discussing about the hierarchical scan approach. So here you will be having around the 4K props are there in level 3 projects. So here in level 3 projects, we will be doing the IJTAG and MBIST insertion, then EDT OCC insertion, then scan insertion, ATPG, simulation. So all these things we will be doing it in our level 3 projects. Is the hierarchical scan approach. So around 10 memories, around 10 memories are there in this level 3 project, and around 4K flops will be there. And level 4 projects, it is a top-down approach. So here we are having around 44K flops and around 50 memories are there. So for, again, the same things, JTAG, BIST, OCC scan, ATPG simulation, so all these things will be performed for our level 4 projects also. Okay. So this is how our labs are structured. Okay. So first we are having level 1 project, small test cases, 11 test cases we are having, where we'll be performing scan insertion. So second level we will be having scan compression. Second level we are having EDT insertion, that is scan compression, then ATPG simulation for the same 11 test cases. And then third level we are having the hierarchical scan approach, where we will be having around 4K, much more complex design. So we are having around 4K flops in our design, and we'll be performing the JTAG and MBIST insertion, EDT, OCC insertion, scan, ATPG simulations, all these things we will be performing. And level 4 projects, we'll be doing the top-down approach. So we are having around 44K flops in our design. So it's a top-down approach, and we will be doing all these processes. We will be doing it there. Okay, in our level 4 projects. So around 50 memories are there in our level 4 projects. So level 3 and level 4, they are designs with higher complexity. Okay, so this is how our labs are structured. Okay, for boundary scan, we will be covering only theory. We don't be covering labs, because for boundary scan, we don't have the license. Okay, we are not having the license for boundary scan. So we will only be covering the theory of boundary scan. We will not be covering the labs. And then the tools which is used for DFT. So these are the various tools which will be used for DFT in the industries. These are the tools which is available. Okay. So in our institute, we will be using the mentor graphics tools, okay, during our course. So for MBIST insertion, we will be using Tessent MBIST. For scan insertion, we will be using the Tessent scan. For scan compression, we'll be using Tessent test compress. For ATPG, we will be using Tessent test compress. For simulations, we will be using QuestaSim. For synthesis alone, we will be using Synopsys tool, which is the DC compiler. Okay, all the other tools are mentor graphics, Tessent tools. Okay, for MBIST, we'll be using Tessent MBIST. For scan, it is a Tessent scan. Scan compression, it is Tessent test compress. ATPG, it is Tessent test compress. And simulation is QuestaSim. Okay, for synthesis alone, we will be using Synopsys tool, which is a DC compiler. Okay, DC compiler. So at one stage, we need to perform synthesis. So during our labs, so for that, we will be making use of the design compiler Synopsys tool. Okay. You can attend this course. So if you are in a if you are a student who is there in the final semester, and you are seeking DFT as your course curriculum, you can enroll for this course. Or as a new college graduate, you are a new college graduate, you are from relevant branches of engineering or science, like EP, E&I. So if you are in the relevant branches of engineering and science, you can take up this course. Lecturers or professors who want to switch their career into real-time industry experience. So if you are like in VLSI domain, if you are like a professor in taking some VLSI subjects, and if you want to switch to real-time project, real-time industry experience, if you want to switch, then you can take up this course. Even working professionals from similar or other VLSI domains. So say for example, you are working in front end, like functional verification, you are a functional verification engineer, but now you want to learn DFT. So you want to like switch your domain to DFT. You can attend this course. Or else you are a physical design engineer, but you want to switch your domain to DFT. You can also enroll for this course. Or else you are working in some IT company and you want to switch to VLSI domain, VLSI company, if you want to switch, then also you can attend this course. And placement support. So we are having tie-up with various VLSI companies. So students are entitled to placement support based on the performance in the course assignments. So during the course, we will be giving you some assignments, some mock interviews, and some tests. All those things will be conducted, presentation sessions. So all these things will be conducted. So based on your performance in all these tasks, you will be allowed to attend for placements. Okay. So mock interviews will be conducted. Okay. So previous company interview questions and preparation. So previous company, whatever interview questions were asked, So those questions will be discussed along with the answers during the sessions. Okay. So yeah, this is how we will be providing the placement support. Okay. So that is it. Does anybody have any doubt which you want to ask?
Ma'am, what are the class timings?
Class timings, like it will be informed to you in your individual, one DFT group will be actually created for you. In that group, they will be posting the session timings. So like, or else there will be a individual group which is created. So is an individual group created for you with your name and VLSIGuru ID is an individual group created for you. So if you post it in that group, so like they will clarify you regarding the session timings and as well as when the course starts. So all those kind of informations, like from admin team, they will be like giving you the details. So do you have an individual group which is created with your name and your VLSIGuru ID?
No, ma'am, not yet.
Okay, then I'll share with you the details of admin team. So you can contact them. They will let you know about the class timings. Okay, and then the like when the course starts. So those kind of details. I'll share the number. Just a second. So this is Manohar sir's number and Usha ma'am's number. So if you contact them, they will tell you the exact timings of the course, the schedule, and then when the course will be starting. So all those things will be, you can contact them. Or if an individual group is created already, you can message in that individual group directly. So admin team, they will contact with you and they will tell you these details. So basically, like when the course starts, so you will be added to a DFT group where all the students of your batch will be there in that group. At the beginning of every week, they will be posting the schedule for that particular week. It will be posted there. So if you want to know now itself, like you can contact Manohar sir or Usha ma'am, or else if an individual group is created, you can post it in that individual group. Manohar sir or Usha ma'am will be addressing it. Any other questions you have? For the first 2 months or 2.5 months, basics will be covered. So where digital design, Verilog, CMOS, Tickle, Linux, all these topics will be covered. So in the initial beginning 2 or 2.5 months, the basic training will be happening. Once the basic training has been completed, you will be coming to this advanced DFT course, the DFT syllabus, whatever I have discussed, so that we will be discussing for the next 3 or 3.5 months. So the total course duration will be 5.5 months or 6 months. Okay. So initially you will be having the basics training. So you will be starting with GWIM training, digital design, Verilog, Tickle, Linux, CMOS. So all these things will be covered. After that only we will be starting the DFT course. Okay. Any other doubts do you have? Okay. So if there are no doubts, shall we end our session? So if you have any query, like you can post it in your individual group. Okay. So like technical staffs as well as admin members will be there in that group. So we will be addressing the queries. So an individual group will be created shortly for you. You can post in that group as well. Yeah. Thank you all. We will end today's session.